In this third session of projectile motion, we will talk about two special problems that are typically not covered in high school physics. We already covered the basics of projectile motion, 1D and 2D, in the earlier sessions. If you haven't seen them, you can find their links below. So, let's get started. When talking about projectile motion in introductory physics, we often assume that there's no air resistance, gravity is the only external force on the projectile, and it's constant. These assumptions are good approximation for a lot of problems, but there exist some situations where these assumptions no longer hold true. High-speed projectile is one such example where Earth gravity should not be assumed constant because the projectile travels significantly farther away from the Earth's surface. So, let's take a closer look at this high-speed projectile problem. Before we delve into it, we need to take a quick look at how we come to this gravity term, g. To do that, we start with Newton's law of universal gravitation between two bodies. It says, there exists an attractive force between two objects, proportional to the masses of and inversely proportional to the square of the distance between the two objects. Graphically, you can see it here. Object 1 has a mass of m1, and object 2 m2. They are a distance r apart from each other. A force, an attracting force, F, exists between these two objects, and mathematically it can be expressed as F equals the gravitational constant, capital G, times m1 times m2 and divided by square of the distance, r. The gravitational constant is an experimentally determined tiny little number, and it should not be confused with the lowercase g, which is the nominal Earth gravity or standard gravity. Now, what do we know about Earth? It has a radius of over 6,000 kilometers, and a mass close to 6 times 10 to the 24th power kilograms. We use m2 for Earth, and m1 would be the mass of an object on the Earth's surface, like you, me, falling leaves, or any object. Then, for that m1 object, using F equals ma, we have the acceleration due to gravity g equals F divided by m1, which, according to the universal gravitation formula, equals capital G times m2 over square of r, or Earth mass over the square of Earth radius. Plug those numbers in, we got approximately 9.80 meters per second squared. That is how we have the standard gravity g at 9.80. This 9.80 number is only good on the Earth's surface, because we used the Earth radius as the distance between Earth and the object. The minute you are moving away from the Earth's surface, the little r in the equation is no longer just the Earth radius. It's the Earth radius plus however far away you are from the Earth's surface. And it's to the second power of that combined distance, meaning the gravity would decrease rather quickly as you move away from the Earth's surface. Let's now try a real problem. We give it a large initial speed of 6 kilometers per second, which is 6,000 meters per second, and want to determine the maximum height the projectile can reach and the time it takes to reach it. In this example, we still assume there's no air resistance. Let's first use a constant g of 9.80 meters per second squared to see if it's a good approximation. Since this is a 1D problem, we have velocity equals the initial velocity minus g times t, and the position, y, equals the initial position, which is 0, plus the initial velocity times t minus 1/2 of g times t squared. We know velocity is pointing upward in the beginning, and decreases because of the gravity, eventually becomes 0 when it reaches the maximum height. So, to find the time to reach the maximum height, we simply set velocity, v sub y, to 0, which is the case at the maximum height. The time, t, to reach the maximum height becomes the initial velocity divided by g. Plug in the numbers, we have 612.24 seconds. Knowing the time to reach the maximum height, we can now use the second equation above to find what the maximum height is. It equals 0 meters, the initial position, plus 6,000 meters per second, the initial velocity, times 612.24 seconds, minus 1/2 of 9.80 meters per second squared times the square of 612.24 seconds. This comes to approximately 1,836,735 meters. A quite large number. Using Newton's law of universal gravitation, we can now examine what the actual Earth gravity is at this height to see if it is close to the 9.80 number we assumed. If it is, then the constant g is a good assumption, otherwise, it's not. As you can see, it turns out that the gravity g at this altitude is only 5.91 meters per second squared, far smaller than 9.80. Therefore, we cannot assume constant g in solving this problem. Let's continue with the same equations for velocity and position in this 1D problem. The only thing that we do differently next is we have gravity g be a function of position y, based on the universal gravitation formula. The little r equals Earth radius plus the vertical position y. We now have an equation that tells the relationship between time t and vertical position y. With small time increment, we can numerically obtain the vertical position y. Here's a plot of the vertical position over time, with the yellow line being the actual trajectory, compared with the red line that assumed a constant g of 9.80 meters per second squared. The maximum height turns out to be over 2.56 million meters, compared to 1.84 million meters when g is assumed constant at a value of 9.80 meters per second squared. The time it takes to reach the maximum height is also much longer, about 960 seconds. This is a result of the decreasing gravity as the projectile moves farther away from the Earth's surface. Big difference indeed. Now you know how to solve the projectile motion problems where gravity g is varying. The underlying principle stays the same, governed by the two basic equations for position y and velocity v sub y. Next, let's look at a different situation where the air resistance is not negligible. Suppose we have an airplane cruising at 10 kilometers altitude, an object from the plane falls off, and we would like to know what the velocity is when the object reaches ground. We know the final position is 0 meters, ground, the initial vertical position is 10,000 meters, and the initial velocity is 0 meters per second. 10,000 meters is close enough to the Earth's surface, so we can assume that gravity g is constant at a value of 9.80 meters per second squared. If we assume also that there is no air resistance, then 45.18 seconds later, the object will reach the ground at a speed of 442.72 meters per second. This is far from the real situation because air resistance plays a significant role. At high velocity, or sometimes you hear the term high Reynolds number, the drag force acting on an object is against the direction of its motion, and takes on the form F sub d equals 1/2 times air density, rho, times velocity squared times a dimensionless drag coefficient c sub d, and times the area of the object A. With the drag force included, the falling motion is thus governed by the differential equation of dv over dt equals g minus rho, c sub d, and A over 2 times mass m, times v squared. And the solution for velocity v is in the form involving a hyperbolic tangent term as listed here. Since the hyperbolic tangent has a maximum limit of 1, as time increases, the velocity v will approach a maximum value called the terminal velocity v sub t. And this v sub t equals square root of 2 mg over rho c sub d A. The terminal velocity will depend on the mass and area of the falling object, and typically can range from about 10 meters per second to 100 meters per second, certainly a lot smaller than the initially estimated speed of 442 meters per second without air resistance. If a person jumps off the airplane, the terminal velocity can reach about 60 meters per second before the parachute opens. Once opened, area A is increased drastically, and the terminal velocity decreased to 5 or 6 meters per second. If you are interested in learning more about example, you can search up the term fluid dynamics and drag force to gain a more in-depth understanding of air resistance. That's all we have for now. In this session, we discussed a couple of special projectile motion problems where either the gravity g is varying or the air resistance plays a large role. I hope you enjoy the session and find yourself down the rabbit hole of projectile motion and physics in general. And if you like what you see, please hit the like button, subscribe, and share. Thank you.